In this video, we're going to be talking about how we measure how acidic or basic a solution is. So you've probably heard of pH before and discussed it in previous science classes. So we will be talking about pH, but there's also a complementary and less commonly used scale known as pOH that is very similar. They go hand in hand, so we're going to talk about those two things together. So both pH and pOH measure how acidic or basic a solution is. They measure the relative acidity or basicity of a solution. So remember that one of our definitions of acid and base relied upon the concentrations of hydronium and hydroxide in solution and how those were affected. So an acid is anything that generates hydronium in solution. And a base is anything that generates hydroxide in solution. So essentially, pH is measuring hydronium and pOH is measuring hydroxide. And those two things do go hand in hand, which we'll talk about a little bit more in the next video. You can actually convert between the pH and pOH scales. But either one by itself gives us essentially the same information, just in a different way. So both of these are based on a logarithmic scale, base 10 logarithm. So that means that if your pH changes by 1 pH unit, that means that your hydronium concentration has changed by a factor of 10. So what seems like a relatively small change in pH can actually be a pretty substantial change in your hydronium concentration. So mathematically speaking, finish my thoughts, logarithmic scale. So mathematically speaking, the pH of a solution is equal to the negative base 10 logarithm of the hydronium ion concentration. Sometimes you will also see this written as the negative log of the hydrogen ion concentration. These are the same thing. H plus does not actually exist in aqueous solution. So although this is a little bit simpler to think about, and hydrogen ion concentration and hydronium ion concentration are effectively interchangeable, it is better to use hydronium since that's more accurate. pOH is exactly the same thing, just based off of the hydroxide ion concentration. So the pOH of a solution is the negative base 10 logarithm of the hydroxide ion concentration. If we want to go in the other direction, we want to calculate the hydronium or hydroxide concentration from the pH, the inverse function of a logarithm is an exponential. So this would be, our hydronium concentration would be 10 to the minus pH power. Our hydroxide concentration would be 10 to the minus pOH power. So these equations are ones that you are going to be using a lot, allow us to convert between concentration of hydronium or hydroxide and pH or pOH, respectively. So let's try a few practice. So if we have a hydronium ion concentration of 1.4 times 10 to the minus 6th molar, and we want to find the pH, that would be the negative log of that concentration of 1.4 times 10 to the minus 6th, which would be a pH of 5.85. If we want to go the other way with it, if we have a pH of, let's say, 8.42, and we want to find the hydronium concentration, we do 10 to the negative pH, so 10 to the negative 8.42, which is 3.8 times 10 to the negative 9th molar as our concentration. So as long as you recognize these relationships, you're just plugging into your calculator to solve. So I'm going to have you guys try the pOH versions. So if we have a hydroxide ion concentration of 9.7 times 10 to the minus 12th, I would like you to take a moment and calculate the pOH. And if we have a pOH of 1.46, I would like you to calculate the hydroxide ion concentration. So please pause here for a moment and try those two on your own. So we just need to apply these same relationships. pOH is the negative log of the hydroxide ion concentration. So we'll do the negative log of 9.7 times 10 to the minus 12th, which gets us a value of 11.01 for our pH. With significant figures, things get a little weird in the realm of logarithms. I will not hold you to this to any extent on quizzes and tests. But if you're curious, the way that sig figs work when logarithms are involved is that the number of sig figs in this number, whatever you're taking the log of, become the number of digits after the decimal place in your answer. So because we have 2 sig figs in the concentration value that we're given, that means we should have 2 digits after the decimal place in our answer. In the other direction, opposite is going to be true, that we have 2 digits after the decimal place in our pOH, so we should have 2 sig figs in our concentration. It's a little weird, which is why I don't hold you to it. But so calculating our hydroxide ion concentration, we'll do 10 to the negative pOH, or 10 to the negative 1.46, which is 0.035 molar for our concentration down here. So what pH and pOH are measuring is how acidic or basic a solution is. So you probably know some things about the pH scale. And most of them are kind of the same but backwards for pH. So pH and pOH are most commonly between 0 and 14. But please note that values outside of this can exist. You can have negative pH. You can have pH above 14. It's just not very common. Those are the extremes of how acidic and how basic something can be. So they don't happen a lot, but they can happen. They're not physically impossible or anything. 0 to 14 is just kind of the common range where things tend to lie. So you are probably already aware that when something has a low value for the pH, we consider it acidic. And when it has a high value, we consider it basic. And you have most likely been told that pH 7 is neutral, but that is only true at room temperature. That is only true at 25 degrees Celsius. pH actually changes with temperature, and we'll talk a little bit more about that later on. So this idea of high and low is more important than specific numerical values. And what actually defines when a solution is acidic, basic, or neutral is the relative amounts of hydronium and hydroxide that are present in that solution. So a solution is considered acidic when the concentration of hydronium in that solution is greater than the concentration of hydroxide. We have more acidic stuff than basic stuff, so the solution is acidic, regardless of what your pH is. So low pH, specifically less than 7 if we're at 25 degrees Celsius, which is where we will do most of our practice, represents an acidic solution. For pOH, it's the opposite. So a high pOH greater than 7 at 25 degrees Celsius is acidic. A solution is considered basic when the hydronium concentration is less than the hydroxide concentration. We have more basic stuff than acidic stuff, so the solution is basic. High pH greater than 7 at 25 degrees Celsius is basic. And low pOH, less than 7 if we're at 25, is basic. So what it really means for a solution to be neutral has absolutely nothing to do with the pH specifically. A solution is neutral when the concentration of hydronium is exactly equal to the concentration of hydroxide. So this occurs at pH 7 as well as at pOH 7. It really happens when the pH and the pOH are equal, which is equal to 7 for both of them at 25 degrees Celsius. So these are better definitions for what it actually means for something to be acidic, basic, or neutral. Usually when I ask students, at the beginning of this unit, what does it mean for a solution to be acidic? They tell me low pH. And when I ask, what does it mean if a solution has a low pH so that it's acidic? Kind of a circular definition here. So this is what it truly means in terms of concentrations for something to be acidic, basic, or neutral.